Now I can take the tensor product of these two things, right? So do you know what a tensor product is?
I've come across it, but I'm not completely comfortable with it.
I saw in the quantum computing that the two vector spaces are like adding up. So 4 cross 4 becomes 16 dimensional vector space.
Yeah. So we just multiply stuff. It's easy as that. So essentially, the result of this would be some kind of an object with two index, where the object with the two index, the mu nu component would be simply the mu component of this guy and the nu component of this guy. Okay, this is as simple as that. Okay. So this is multiplication component wise. Okay, Saif? So if I had, say, this as a vector, and I took the tensor product with, say, 1 and 3, then the result would be, I would have this multiplying this and this, so I'll have half, 3 half, and then I'll have minus half, minus 3 half. Okay, so this would be that tensor product.
Sir, can the tensor product also be represented as square matrices?
Sorry?
Can the tensor product result be also represented as a square matrix instead of like?
Yeah. Yes, you can. And in fact, we are going to do that, in a minute. Yes, it's a very, this is basically a flattened version of this guy. Yeah, because this looks like a matrix, right? But you can say, okay, I'm just going to flatten this guy out. So yeah, there are many different ways that you can write this. So I think so for example, this is like the 1 component, and this is like so you could have also written it like this, that this times this is half, this times this is 3 half, whereas this times this is minus half, and this times this is minus 3 half, right? Yeah. In fact, for us, this is basically, I think that the right way of looking at it, the natural way of looking at it will emerge. So now, if I make a Lorentz transformation, we know that V mu goes like lambda mu nu, V nu, and W mu goes to lambda nu, mu nu, W nu. So now question is, how does T mu nu transform? So T mu nu, because it's we should transform like lambda mu rho, lambda nu sigma with 2, because each of these factors give rise to 1 factor of lambda, and so this will be rho sigma. Okay, so here we see that we have built a rank 2 tensor representation of SO1, 3 from 2 vector representations of SO1, 3. Okay? But it turns out this is not a irreducible representation. Okay, so as Nahi was saying, let's count how many components T mu nu has. Can someone tell me a number of components this guy has?
Mu times nu.
16.
How many values does mu take? Who said 16?
Saif.
Yeah, 16. Because mu takes the value 0, 2, 3. Nu takes the value 0, 2, 3. Okay, so what we can do is we can then organize this mu nu into 3 different groups. One would be, we can organize them into the anti-symmetrization of the indices. Okay, so can somebody tell me what would be the number of elements here? Okay, we'll do the counting a bit later. So we can do anti-symmetrization, that's one representation, and another one is we can do a symmetrization, right? But it turns out that if you do the symmetrization, that itself is not irreducible. And the reason is the following. Lambda delta, eta mu nu is a rank 2 tensor, okay? But it's a special rank 2 tensor. It's what is known as an invariant tensor. Because under Lorentz transformation, like any generic tensor, this will go to this. Okay? But we know that the Lorentz matrices must satisfy the condition where this contraction should give me eta mu nu, right? Because that is the definition of the Lorentz transformation, remember? So this is a special tensor called an invariant tensor. Okay? So invariant tensors are useful because we can use them to construct other tensors. So now if I say T mu nu, eta mu nu, if I do this will tell me that if I compute this thing, that this tells me that this new index will go down and then contract with this. So this has no free index, right? Is it clear why this doesn't have any free index? Because I'm summing over both. So let's call it T, something that should not have an index. Now, if I do a Lorentz transformation, then T mu nu, the other thing is that whenever I contract 2 indices with another object with 2 indices which is symmetric, then automatically these indices will also be symmetric. Okay, this is easy to show because T mu nu is T mu nu, but eta mu nu is symmetric, so we can write this as eta mu nu, right? With the brackets around mu nu. And you can show that that is the same thing as writing this. Okay, so this thing is T. We are defining this thing as T. And this doesn't have an index, which should be consistent with the fact that under a Lorentz transformation, this should be a scalar. It should be invariant. Let's see if that happens. So under Lorentz transformation, T mu nu, eta mu nu should go to lambda mu alpha, lambda nu beta, T alpha beta But we have already proved that this thing does not change under Lorentz transformation. This thing should just remain eta mu nu. But then eta mu nu contracting with this thing should just give me eta alpha beta. Contracted with eta alpha beta, but this thing is nothing but this thing. So this, we call it T, and we see that under Lorentz transformation, T goes to T. So T is a scalar representation of SO1, 3. Now, if I go back to this discussion, we see that, you know, of the whatever number of components this has, the scalar part of it is a separate, representation. So we have to subtract it. So what do? We have to subtract it in a way such that, you know, the overall rank 2-ness of this tensor doesn't remain unchanged. So we subtract minus T and eta mu nu, we multiply it by this. But now if I take the trace of this, the trace of this gives me 4. So I should divide the whole thing by 4. And this whole object is then now an irreducible representation. And number 3 is T. So T mu nu is not an irreducible representation, but one can show that the antisymmetric part, of course, is automatically trace-free because there is no diagonal elements, and the symmetric part minus the trace properly normalized and the trace part. So these are the 3, you know, irreducible representations. So we can write T mu nu in the following way. So we can write, say, T mu nu in a way where basically we have a 16 by 16 matrix, but then we have a 4 by 4 part, where, you know, this is, let's just call this E1, E2, E3. I'm just giving them random names. B3 minus B2, B1, minus E1, minus E2, minus E3, minus B3, B2, B1. Okay, so this is the part, which is the, so this part is the T antisymmetric, you know, mu nu. Okay. Okay, so how, right, so, and then we have another part, which will have, say, T1, T2, T3, T4, and then whatever we write here will be exactly the same here. So this will be symmetric, but T1, T2, T3, T4, T1, T2 plus T3, T4 will be 0. So only 3 of these guys will be independent, and the trace of, you know, so this will be basically T mu nu symmetric minus eta mu nu by 4 T, and here we will have T. Okay, so this is basically how the vector space on which the Lorentz transformations act will decompose. And the idea is that under Lorentz transformation, you know, this thing will go unto itself, and this vector space will go unto itself, and this vector slash scalar space will go unto itself, and they will not mix with each other. Okay?
Doesn't this matrix have 17 rows then? Sorry, no.
Yeah, I mean, superficially it does, yes. But if you count the number of independent components it has exactly 16, right? Because here you have 3 and you have 3. So here we have 6. So here what we have is that we have a symmetric 4x4 matrix, right? A symmetric 4x4 matrix has 16 components, but it's symmetric. So if we subtract 4, which is the diagonal element, and divide by 2, those are that's the number of independent diagonal elements, right, Saif?
Yeah.
Oh, sorry, off diagonal elements, right? And in the diagonal elements, there are superficially 4, but they have to, satisfy this condition. So this will be, so we add 3 here. So what do we get? We get 16 minus 4 is 12 by 2 plus 3. So we have 6 plus 3, 9. And then we have 1. So we had 6 plus 9 plus 1, which is exactly 16, okay?
Yeah, makes sense.
Yeah. So that's the idea, is that from smaller representations, you make bigger representations, but in a way that they map onto themselves. So I gave you an invariant tensor eta under, say, SO1, 3. Can somebody tell me what the analogous invariant tensor under SO3 should be?
So the Euclidean metric.
So it should be delta ij, right? And of course, delta ij under a rotation is IL, JK delta LK, and this has to be equal to IJ, and this is nothing but the statement R transpose R is 1, which is the O3, or yeah, okay. So let me give you another example of an SO3 invariant tensor.